Everyone, welcome back to today's video. And in the last video, due to some technical glitch, I could not discuss misconceptions about p-value. It stopped recording in between, so we are discussing the misconceptions today. So the first misconception is that higher p-value means that I am accepting the null hypothesis. This is not the case. A higher p-value shows that data is not statistically significant, but that just means that we fail to reject the null hypothesis. That does not mean that we are accepting the null hypothesis. Let me explain you why. Accepting the null hypothesis means that I am conclusively saying that there is no effect of the drug or the two groups are not different. So I am conclusively saying that my null hypothesis is true. That is accepting the null hypothesis. So higher p-value just failed to reject the null hypothesis because there can be many reasons for the higher p-value. Like we didn't take enough sample size, there may be bias and there may be beta error. We will talk about this in a separate video. So if we didn't have enough sample size or there was a bias or there was a beta error, we get a higher p-value. Even if our data is even if our study is successful, we may get a higher p-value. So if we conclusively say that I am accepting the null hypothesis, I am closing all the doors for future. So I don't have any room to improve the sample size, take a larger sample size or improve the bias or beta error. That is why we never conclusively say that the effect is not there, because we want to keep the door open. We want to improve our study design. That is why a higher p-value just failed to reject the null hypothesis. Keep that in mind. A statistically significant result doesn't prove that it is not due to chance. So if the data says if the p-value is less than 0.05%, there can be still a room for chance. That chance is 5%. So there is still 5% probability that results are due to chance or luck or random error. If we would have said that we only reject null at p equal to 0, then we would have removed all the probability of chance or luck. So because we are accepting that we will reject the null at p less than 0.05, we are saying that I am okay to accept the chance element up to 5%. This is called alpha error, by the way. So there is a question that why don't we choose p value equal to 0, that I will reject the null only at p value equal to 0. If p value measures chance, then I want to remove all the factors of chance, and if my p becomes 0, if I get a p value equal to 0, I will design my study in such a way that p equal to 0, then I will be good. But we cannot do that. We cannot totally negate the chance. This comes as a question, can you totally remove the chance factor from your studies? No, we cannot, because we need to leave the room for chance, as there is a trade-off between alpha and beta error. Alpha error and beta error. So what is an alpha error? If there is no actual effect of your drug, if there is no actual effect of your drug and the data is showing as clinically significance, that is alpha error. So why will data show the statistical significance? If your drug has no effect and your data is showing as statistically significance, then that is alpha error. Why it will show that? It will show purely because of chance, right? Purely because of chance. So alpha error measures chance and beta error is opposite. Beta error is if your drug has a real effect, it reduces the blood pressure, but the data is showing as not statistically significant. So alpha and beta error we will discuss in a separate video, but these are opposites. So there is a trade-off between these. So if I take p-value as 0, which measures alpha error, then beta error will increase a lot. I don't want that. Because beta error says even if there is effect, even if there is effect of the drug, my data will show not statistically significant. So if this error increases, what is the point of doing the study? So that is why we don't take p-value as 0. We accept it at 5%. But it still has a probability that results are due to chance. This probability is 5%. So I hope it is clear. P-value doesn't measure the strength of strength or size of an effect. So it means that if we get a very small p-value and we have a large sample, then a small effect can give us a a, so a small effect can give us a very small p-value. So let me say that again. So if we have a very large sample size, even a minor effect, a small effect can give us a very small p-value. So even though the effect is small, effect of the drug is small, a small p-value means that we have statistically significant data, significant data. But in actuality, there is a small effect. But why we are getting a very small p-value then? Because we have a large sample. That is the only reason. Similarly, if we take a very small sample, even a large effect of the drug or a large variation can give us a very large p-value and our study will fail. So p-value changes with sample. What sample size do you take? So here what we are seeing that there is small effect but our study is clinical significant. Large effect but our study is clinically non-significant. This is due to samples, right? The number of people we have studied. So p-value does not measure the strength or size of the effect. Then how do we measure the effect size or the strength? By different metrics, that is mean difference, relative risk, odd ratio, confidence interval, and all these things. So I have a video on risk quantification where I have discussed this. So if you want, you can go back and check that. Another misconception is that p-value measures clinical significance. No, it only measures statistical significance. It doesn't measure clinical significance because clinical significance measures the magnitude. Clinical significance depends on the magnitude of the effect. For example, if there is a reduction of 0.8 mmHg in BP by taking a drug, will it be clinically significant? No, but it can be statistically significant. So clinical significance depends on the magnitude of the effect. Okay, so data can be statistically significant. Data can be statistically significant, which is measured by p-value, but it is very much possible that there is no clinical significance. So confidence interval should contain meaningfully clinical significant values. So what is confidence interval? Suppose you conduct a study and you get 10 mmHg reduction in blood pressure in your study. Okay, and your friend comes in and he says that if I conduct this study a million times, then will I always get 10 mmHg? And you say no, you might get 9, you might get 11. So he will say that then how you are saying that your drug reduces the BP by 10 mmHg? So you are thinking, yes, he is right. So you always actually give the results of your study in a range, not as a value. You will say that if you conduct the study 1 million times, then 95% of the times your reduction in BP value will fall between 9 and 11. So that is called the confidence interval. This is the 95% confidence interval and 9 to 11. That is how it is. So confidence interval should contain meaningful clinically significant values. 0.1 to 0.9 mmHg confidence interval is not clinically significant, but 10 to 12 mmHg is. So I am saying the same thing that I've said here in terms of confidence interval here. We will discuss confidence interval in another video. Then how should we measure clinical significance? We should assess the real world impact like improvement in systems, reduction in mortality, quality of life improvement. All these real world impacts should be measured and then only clinical significance can be proven. So what are the assessment of absolute measures like absolute risk reduction, number needed to treat? Again, I have explained this in risk quantification video. So please go and check that video. So that's from my side, and I'm again sorry for the technical glitch that happened yesterday. I will take care of that in future. So if you like this video, please like, share and subscribe, and I will see you in the next video. Thank you.